Now I can show you a method. You can take any permutation and you can rewrite it in the form of a product of disjoint cycles. So I've left it blank here. I want to show you how it's actually done, so you'll see me doing it live, so to speak. Right. So here's an arbitrary member of this set, the symmetric group of the permutation operations on eight objects, and this is just one of, God, how many? Huge number. The number of members of this set, or group, will be 8 factorial, whatever that is, a large number. Anyway, okay, so how to factorize, well, that's the right word, how to rewrite this permutation in terms of cycles, and they will disjoint cycles. Remember, 2 cycles are disjoint if there's no term in common between the two. There's no integer that's in both cycles. So this is how it's done. Okay, well let's start from the right hand side and we'll work through from left to right, and you'll see what I mean in a minute. Okay, so 1 goes to 2. So oh, and by the way, we're creating cycles. So I shouldn't be starting here. I should be starting here. The right, when you apply sequentially permutations, you do permutation 1, then permutation 2, and so on. The first permutation is on the right. So my first cycle I should put here. Okay, so 1 goes to 2. So 1 goes. So 1 goes to 2, and then 2 goes to 4, and 4 goes to 1. So we've got a cycle there. Okay, so 1 goes to 2, 2 goes to 4, 4 goes to 1. So 1, 2, 4. So I can eliminate those 3. We've done those 3. All right. Now start on the next unused, uncrossed out one, if you like. So there'll be 3. So this will be the second cycle, the second permutation. So 3 goes to 5, 5 goes to 7, and then 7 goes back to 3. So there's another cycle. Oh, sorry. You got the 3. Okay. 3 goes to 5, 5 goes to 7, 7 goes to 3, back to 3. Right? Okay, so we can eliminate those. And so we're just left now. So 6 goes to 8, and 8 goes back to 6. So here's 6, 8. Okay. So we have now taken an arbitrary permutation, and we've expressed it as the product. Do this first, then this permutation, then this permutation, then this one. So the product of 3 cycles, and these are cycles. So in the permutation, 1 goes to 2, 2 goes to 4, 4 goes to 1. It's a cycle by definition. Right? 3 goes to 5, 5 goes to 7, 7 goes to 3. You get all that from here. 6 goes to 8, 8 goes to 6. Okay? Now, proving, in the text, theorem 43 is just this theorem, and the proof is not given because it's tedious and long. And remember, I suppose it's fair to say, this is a junior, senior, or no, in senior level course by Barnard, the first author, and the second author. The poor second author doesn't get a mention. So he can't do everything at undergrad level. So he leaves some things for higher levels. So no proof. Proof is tedious. Okay, not in the text. All right. Now let's do something similar to this again, but this time with one difference. Notice all these pairs, all these mappings. They're all the integer underneath is different from the one above, but in this case we've got one similarity. I mean, one, they're the same. So this 6 So what effect, when that happens, what effect will that have on your cycle product, the product of cycles? Well, let's find the cycles. So 1 goes to 2, 1 goes to 2, 2 goes to 4, 4 goes to 1. Okay, so there's one cycle. It should so just check that. 1 to 2, 2 to 4, 4 to 1. No, I don't need the 1. No. Okay, made that mistake before. Okay, so there's one cycle. Alright, so 1, 2 and 4 we're done. 1, 2 and 4 we're done. Alright, so going from left to right, so 3 will go to 5. 3 go to 5, 5 goes to 7, 7 goes to 8, 8 goes back to 3. Okay, so we need all this space. So there's your product of cycles. Now look, it's this permutation is among, it's permuting 8 objects. So it'll be a member, let's say, of S8, symmetric group of 8 objects, and the 6 doesn't change. Now look, if you look at these numbers here, 1, 2, 3, 4, 5. That's all there. The 6 is not mentioned. 7, 8. Now, when that happens, if you see this kind of thing, say a factor of, product of cycles, and you notice one or more of the members of your objects, if one's missing, like the 6 is missing, what that means is that it maps to itself. So if you're expanding this out to get this, and there's no mention of 6 here, well, you just map it to itself. Okay, that's the convention. So pay attention to missing, in a sense, missing terms. All right. Okay. Now, as a bit of homework, I ask you to do this yourself. You're given this permutation, and it's again a member of S8, the symmetric group of 8 objects. Okay. So X belongs to this group, and you're asked to write out X squared. So you'll just do this twice, okay? And to find the inverse, well, we've done that before, so you know how to find that. So you get the result, X squared, the 2 brackets, 2 sets of brackets. So this times itself, and you'll get something, you'll get another transformation, something in this form, and then you're asked to rewrite that product, X squared, as a product of disjoint cycles. So you'll do this kind of exercise again. You'll end up with something like this, right? And similarly the inverse. So find the inverse of this. So we did that a bit earlier. Get the result, find the result, and then do this kind of thing to get the inverse as a product of disjoint cycles. Right? Now, Barnard just notes, he says, if you'll find that the answer to that and the answer to this are equal. Right? And the reason that is because the order of this element, it's an element, right, is 3. Right? So that becomes true. Right? That's just a little note, not terribly essential. Okay. Now, so we've talked that completes more or less talk on cycles. Now we move on to a new concept. Well, sort of. It's the idea of a transposition. Trans, like across, pose, to put. So to put across, literally. But the technical meaning of a transposition is that it's a special case of a cycle. It's a particular kind of a cycle. and it's a very small cycle. In fact, by definition, a transposition has length 2. It's a cycle of length 2. Okay, so it'll be of this form, you know, A, or just AB. Right? Like, here you've got a cycle of length 3. Here you've got a cycle of length 4. But if it's of length 2, just, you know, 2 terms, by definition, it's called a transposition. And transpositions are pretty important in future work, future theory in finite groups. Right? So the effect, you know, if you apply a transposition to your set of objects, effectively all they do is, like, A goes to B and B goes to A. So in other words, it's just a swapper. A transposition swaps A for B and B for A. Right? So it just swaps the two around, effectively. Right? Now there's a theorem, and again, no proof in the text. It's again tedious, but what I will do. So the next few lines are not in the text; they're coming from me, just to try to persuade you that this statement here is plausible, at least. I mean, I'll show you that it's true.